Okay, welcome back. Okay, so today I want to clarify some ideas about the derivative. So, we talked about this yesterday and you've done some work with it. Let's clarify what a derivative is. The derivative of a function f of x, so that's the name of the function. So the derivative of the function f of x at x equals a is just, or is simply, the slope of the tangent line to the graph f of x at x equals a. That's it. That's really it. A couple of things I might want to call attention to. Maybe we'll do a quick little diagram of what we're talking about. So there's function f of x. Here's a point on f of x. That's at x equals a. Notice that this particular point, I'm going to call it P for point, is given by a comma f of a. And what the derivative is, it's the slope of the tangent at x equals a, which means the slope of the tangent line, the slope of this line going through this point. And just to be very clear, this point P, which is a comma f of a, is what I call the point of tangency. And it is the point that's shared by both the tangent and the curve. So point P is the shared point. That's what a derivative is. Let's be very clear here. The derivative is a very fancy word for saying it's the slope of the tangent at a particular point, x equals a. Now, we've learned a bunch of things leading up to this and how this is developed, but the actual definition is that it's the limit as h approaches 0 of f of x plus h minus f of x all over top of h. And that has a very distinct mathematical notation. Oh, I'm sorry. This is wrong. It's not x. This is an a. This is an a. Because it's at a point, it's going to change to an x soon. Those are a's. And this is f prime at a. All of this is happening at a point. That's why those are a's there and not x's. We good? Okay. And we say that this means, in words, we call this f prime at a. And all of this, I lose my voice. All of this is predicated on one simple concept, provided that the limit exists. And that's a little ominous. Okay, that's a little scary thing. That's like at the end of a story, someone says, and it could be true. It just makes, that's a little scary. We're not sure what that means yet, but there's something there. Otherwise, we wouldn't be putting it there. And that's going to come up later, as long as the limit exists. If the limit exists, then this definition doesn't hold true. So, and all of yesterday was spent getting this. And I'm tempted to go over how to get it again, but I'm going to lose time if I do. So I'm not going to. We'll leave it at that point. Okay, we'll do it really quickly. So, you don't have to write this if you want. You've seen this 1,000 times. You really don't have to. I just want you to be understanding what's going on. Here's my point P. It's at some value of A. I can't do a slope with only 1 point. It's impossible. We know that. To do a slope, we need 2 points. We understand that. So we have another point here, Q, that's a little bit farther down the road. How much farther down the road? Oh, I don't know, a little bit, say H. And so this new X value is A plus H. Its new range value is going to be F of A plus H. And this new range, this old range value is F of A. Is this making sense from yesterday? We did it 1,000 times. So then what we do is we do the slope of the secant between P and Q, and it's equal to rise over run if you're in grade 9. It's equal to y2 minus y1 over x2 minus x1. I skipped one there. Delta y over delta x. It doesn't matter where they come in, but those are the two ideas, right? So we have to do the difference in the horizontal and the difference in the vertical. The difference in the vertical comes first, so the difference in the vertical is this one, which is y2. This is y1. So it's going to be f of a plus h minus f of a over top of the difference in the horizontal is a plus h minus a, which we learned will always work out to be h. That's the slope of the secant, no matter where I put the secant, right? Starting at A and moving that other point a little bit down. And then along came Newton. That sounds like a song, doesn't it? Along came Newton. And Newton said that the slope of the tangent, therefore, at x equals p will be equal to the limit as that distance, this distance here, that distance gets smaller and smaller and smaller and smaller and smaller and smaller. What's happening is h is getting closer and closer and closer and closer and closer to p. So now we have the definition from above, and I've done it for the 34,000th time now. Are you getting the idea that you better be able to do it? That you better be able to know how to do it? And this is the slope of the secant, and that's what he came up with. And isn't that a beautiful thing? I'm going to stop the video there, and we'll be back in a minute.